Okay, I'm going to spend a little time on this page in your little packet talking about a little bit more on section 2.4, which is continuity. When you have continuous functions, it's very easy to find limits because you actually have a value on the function. So thinking about that, if you look at 75, this is a cubic, which means that if you plug in -1, you're going to get a number that's actually on the graph. That is true for all of these functions. Thinking about this, if you plug in 3, are you undefined anywhere? And you actually are not. So all of these are defined. So if the function is continuous at the number that you're approaching, then the limit of the function is the value of the function. So with that said, I want you to pause the video, actually try to do these with your brain, no calculator, and get your answers, and then play this back and check your work. Okay? So pause it, and then come back and check. Okay. So hopefully you've tried everything at this point, and you're ready to check this page from 2.4, finishing up. Okay, so I actually did the first couple for you, so it wouldn't take all our time. Okay, so the first couple, 75 is -6, 76 is 7, and if you plug in, you get those numbers, okay? So remember on 76, your negative exponent would mean that you would put that in the denominator and make this 12/4, so you'd have 7. Okay, 77 is 1/3, and then I saved the trig work for us to do together. So on the trig work here, on 78, you're doing the sine of pi/2 minus pi, which would give us this, okay, and that's -pi/2. So this value is whatever the sine of -pi/2 is. And so remember, you want to have a good command of your trig. So if you're rusty on the trig, go back and review it. Which means that I should know how to get this value pretty easily without a calculator, using my brain and the unit circle. This is a negative angle, which makes this land here, which makes the sine value 1. This is 1. Okay, or actually -1, sorry. Okay, 79 is the tangent of 3pi/4 if I plug in. So we should be able to locate 3pi/4 on the unit circle and find the tangent. Now, this is pi/4, 2pi/2, 3pi/4 is here. The tangent there is -1. Remember that this point on the unit circle is -√2/2, √2/2, which means the y over the x would give us a negative, and we'd get that. Number 80, if you plug in cosine of pi, cosine of pi would actually be over here on the unit circle. Okay, so we have 1 over cosine pi, which is -1. 1 over -1, you should have -1. Okay? All right, 81. If you plug in 4 here, you actually get 4 to the -5/2. And now you need to know how to do that with your brain. So this means the square root of 4 to the -5. So let me rewrite that. The square root of 4 to the -5 power. Okay? Which is 2 to the -5. Lots of algebra involved here. Which is 1 over 2 to the 5th. Which is 1 over 32. 82, if you plug in, you get 4. That one's pretty straightforward. 83, if you plug in, you get 1 minus 8 times negative 1 cubed to the 3 over 2, which would give us 1 plus 8 to the 3 over 2. So this becomes 9 to the 3 over 2, which again is the square root of 9 cubed. The square root of 9 cubed is 3 cubed, which is 27. Okay? All right. Likewise, at the bottom of this page, you have some functions that are piecewise functions. So if you're dealing with a piecewise function and you plug in the value of 1 and you get the same thing here on the left side as the right side, that means they connect. So that would mean that 1 squared would equal 2 minus 1. So you get 1. Okay? Same thing here. So you're doing these by plugging in to see if you get the same thing. And then if they do, then you know the value. So just to kind of do those quickly, here's the work. I'm going to let you check those. This would be 1 squared is 1 and 2 minus 1 is 1. Because they're the same from the left and the right, the answer is 1. This one, if you plug in 3, you get 3 on both parts, so 3. This would be a limit that does not exist because the limit from the left is 4 and the limit from the right is 9. Does not exist. It's a jump. Here, if you plug in 2, you get 8 for both parts, so the answer is 8. Okay? Now, go ahead and go on over to this page. Okay? This next page, we're going to finish up to 4. We did a good job on that. On this page, I've given you some examples that I'd like you to read through. These are examples of severe discontinuity. They have neither left nor right continuity because if you were to look at the graph on them from the left and the right, it's like the function can't decide where to go. Okay, so the values are shooting up, down, and they're just going up and down and up and down. So because they're doing that, they're really not approaching a single number. They're just oscillating up and down. So these are examples of severe discontinuity. A point dot discontinuity is called a removable discontinuity because the function can be redefined at the point. Okay, if it's jumping around like that, then it's severely discontinuous. Okay, you will also see some problems where you are asked to make a function be continuous. Okay, so here's an example. Use the definition of continuity to find A and B so that F will be continuous everywhere. Okay, so the idea that we just learned was that if you plug in this number into both pieces and you get the same thing out of this part as you do this, it's continuous at that number. So if I can take -3 and plug it into these two values and set them equal, I should be able to make them connect. So to do this problem, you actually say -17 equals A, and in the place of X, we're going to put -3 plus B. So we're connecting this piece to this piece at the number where the transition happens. Okay, now you should notice here, this does not give you something you can solve, which means in order to find the values, we're going to need to make another connection. So at 1, the transition happens between this linear piece and the 3. So we're going to write another equation. 3 is equal to A times 1 plus B. Okay? And then we can actually get A plus B equals 1. A equals 3. And then you have two equations that you can solve in order to find A and B. So the easiest one to solve is this one. So I'm going to say B is equal to 3 minus A. And I'll take this piece and I'll go over here and plug it in right here. And I'll solve. So I'll go negative 17 equals negative 3A plus 3 minus A. And then that would give me negative 4A plus 3. Keep on solving. Negative 17 minus 3 is negative 20 equals negative 4A. So A is equal to 5. Then go back and plug it back in here. B is equal to 3 minus 5. And B would equal negative 2. And then you have your two values. Okay, so pause it and try the next one. And then check yourself when you're finished. Okay, so write yourself an equation. And then I'm going to show you the answer to this one. To solve this one, you're taking 3 and plugging it in for x as you set these two pieces equal. And then you solve. You should get 21. Okay? All right. And then we did not quite finish the last two problems over here. And I'll try to... I'll go ahead and point this one out because we went over the rules for this cubic. When you actually factor this, you get x minus 2 times x squared plus 2x plus 4. Okay, following the rule that we set up in class in your notes. Okay, don't have a copy of that right this second. But you wind up having a hole at 2, and the y value would be 12 when you plug back in. And so here's your graph. This is a removable point discontinuity. Okay, and then let's explore the greatest integer function. We'll look at it in class, how that happens. Actually, let's just go ahead and look at it. On number 8, the greatest integer function is the greatest integer less than or equal to x. So, if you see these brackets written like this or sometimes like that, that implies the greatest integer that's less than or equal to the number inside. So if I take 1 and put it in, the greatest integer smaller than or equal to 1 is 1. If I put 1.1 in it, the greatest integer smaller than or equal to 1.1 is 1. I put 2 in it is 2. So what winds up happening is if I put 1.9 in it, it's still 1. But that would mean that everything from 1 all the way up to 2 with an open circle is going to have a y value of 1. And that continues as you do the points. This is called a step function, and it has a jump discontinuity, and it is non-removable. So that should finish up section 2.4, if you will take time to do that. And then we will continue with 2.6 in our next class.